Hi guys, I'm Monica. I welcome you all to my channel Aerokar. So in our journey of aerodynamics, we will be learning the topic incompressible flow in a duct, where we will learn about how to calculate the flow properties through a duct and how do the flow properties vary in a duct. Now when I am using the term called as duct, which says wherein the moment I say duct, we get a three-dimensional picture of it, correct? So we say that yes, it is something of three-dimensional view. Certainly, yes. So duct is always a three-dimensional shape, for example, a tube or maybe elliptical or rectangular cross sections, which vary in area from one location to another. And whenever we are analyzing a flow in a duct, it is certain that we use only the three-dimensional equation. So in order to analyze the flow, only the three-dimensional equations are used. But here we are going to take one assumption which is valid as well. What is that assumption? Let us have. What happens is, in many applications, the variation of area is only a function of x. That is, the area varies only in the x direction. Rest, it is the same, or it is the moderate variation. So for such cases, we can assume that the flow properties are uniform across any cross section and they vary only in x direction. So this is the assumption we take, which is also observed in many of the applications. So let us sketch out a duct and see how the flow properties vary through that duct. Now here we are considering this duct over here. So as you can see, in this duct we have a uniform flow. Let us say this is our station 1 and station 2. Now the uniform flow that we have at station 1 is different from the uniform flow at station 2. So here area is a function of x, and also all the flow field variables are assumed to be the function of x. So that is, here we have velocity as v1 and here as v2, then density would be rho1, rho2, and pressure would be p1 and p2 over here at the station 2. Now, such kind of flows where the fluid properties or the flow properties are varying only in the x direction are known as quasi one-dimensional flows. So these flows are named as quasi one-dimensional flows. Now, although this flow is an approximation because it is actually 3D, as we discussed a few minutes ago, right? The flow is three-dimensional in ducts, but whatever results we are getting, those results are mostly accurate and we can use it for most of the aerodynamic applications. Now, let us consider the continuity equation in the integral form, which is given by this. Let us say this is our equation A. For steady flow, what happens to this equation? This term goes to 0, which means I am left with the surface integral of rho v ds is equal to 0. So this is our equation 1. Now what I would do is apply this equation 1 at station 1 and station 2 of this duct. So upon application, what is the equation that we get? And over here in this duct, when I say we are applying it to station 1 and station 2, the area is bounded by A1. So here the area would be A1 and on station 2 the area would be A2. Okay, and it is also bounded by the upper and lower walls of the duct, as you can see. So let us write down the equation, and as you can see, we have considered steady flow over here. So keep that in mind when we are proceeding with the derivation. Upon writing it for station 1 and station 2, this is the equation that we get. Now, along the walls, the flow velocity is a tangent. That is, ds is perpendicular to the wall. So when I say ds is perpendicular to the wall, what happens to the term vds along the wall? It becomes 0, which means this term, that is for the wall, integral at the wall rho v ds goes to 0. Let us say this is our equation 3. Now, at station 1, as we said, we have uniform flow in the duct. So across area A1, ds and v are in opposite directions. In case of station 1, that is, ds always points out of the control volume. So when we take a fluid element and sketch over here, as we had done in our previous derivations, we will see that ds is always pointing outside of the control volume. So when it is pointing outside of the control volume, I can write it in this form. The integral can be written as minus rho 1 a1 v1. This would be our equation 4. Now this negative sign, because my ds is pointing in the outward direction of the control volume. Similarly, when we write for station 2 across area A2, what I would get is rho vds is equal to rho 2 A2 and V2. Let us say this is our equation 5. Now, what are we going to do? Substitute these three equations, that is 3, 4 and 5 in this above equation, that is equation 2. Now, from A1, I have rho 1 A1 V1 plus rho 2 A2 V2, and the wall term will be 0, which is equal to 0. Now, the equation 6 that we have got is known as the quasi one-dimensional continuity equation. This equation, it applies to the compressible flow. Now, when you look at this equation, rho 1 A1 V1 is equal to rho 2 A2 V2, what does it state in the physical terms? It states that whatever mass flow is going through the duct is constant. That is, whatever is going in must come out. Now, if I write the same equation for incompressible flow, what happens? For incompressible flow, rho 1 is equal to rho 2. So, I am left with A1 V1 is equal to A2 V2. This becomes our equation 7. And this equation 7, it is the quasi one-dimensional continuity equation for incompressible flow. What does this state in physical terms? It states that the volume flow through the duct is constant, and this volume flow per, that is cubic feet per second or cubic meters per second, is constant through the duct. So the second conclusion that we get from this equation 7 is that when we see that the area decreases along the flow, that is, my flow is in this direction, we have V1 P1 getting in, and you can see that the area is decreasing along the flow direction. This is known as the convergent duct. We call it as a convergent duct. So when we have a convergent duct, what happens is the velocity is increasing, that is, V2 would be greater than V1, whereas pressure will be decreasing, that is, P2 would be less than P1. Similarly, if I have an area which is increasing along the flow, for example, let us consider this section where V1 and P1 are entering. So this is known as the divergent duct. So what happens on the divergent duct? there is a decrease in velocity, that is V2 is less than V1 and P2 is greater than P1. Now, what conclusion do we have from the Bernoulli's equation? From the Bernoulli's equation, what can we observe? So we can observe that when the velocity increases in a convergent duct, the pressure is decreasing, and in the divergent duct, the velocity is decreasing and pressure is increasing. So this is given by the Bernoulli's equation. So now let us consider a flow through a duct, and here what we are going to do is we are going to consider an incompressible flow. Initially we had said that the flow is steady. Now we are going to say, or we are going to assume, that the flow is incompressible. So this is my duct where the flow is entering with the velocity V1 and pressure P1, and here we have the area A1. So this point is called your throat, and the velocity leaving would be V2 and P2. Here you have the area A2. So I have marked this point over here. What is this point all about? Let us have a look. Now, when you see that the flow is entering with the velocity V1 and pressure P1, what happens to the velocity in the convergent portion of the duct? The velocity increases as we have just seen. So what happens is it reaches a maximum value. So in the convergent portion, the velocity increases, reaching a maximum value V2 at the minimum area of the duct. So here you can see this is the minimum area of the duct where my velocity has reached a maximum point, which is V2. And what is this minimum area region? What we have called that as? We have called that as throat. And what happens to the pressure in the convergent section? The pressure is decreasing, as you can see over here in the graph. So this would be my pressure and this would be the x-axis. So this point, what we have marked is the pressure is minimum at the throat. All right, that is P2. It reaches. Now what happens to the flow in the divergent section, that is downstream of the throat? What happens to the velocity in this region? Velocity decreases and pressure increases. As you can see, there is a rise in pressure again in the divergent section. So this duct, what we have seen, is usually called as venturi. Okay, now what is the primary characteristic? The primary characteristic is that the pressure is lower at the throat than the ambient pressure, that is P1, which is outside the venturi. So the pressure here is lower. It is the primary characteristic what you observe in an venturi. Now this pressure difference, what we see, that is P1 minus P2, this pressure difference is used in many applications. What kind of applications? For example, you have the carburetor and automobile engines, right? So we use the venturi through which the incoming air is mixed with the fuel. So what happens? The fuel line opens into the venturi at the throat. Now because we know P2 is less than the ambient pressure over here, so we have a pressure difference P1 minus P2. So this pressure difference will help me to force the fuel into the air stream and mix with the air that is downstream of the throat. So this is how a venturi can be used. This was one of the example that we have seen. Now the other task of venturi is that it can also be used to measure air speeds. So now here let us consider a venturi which has an inlet to throat area ratio of A1, A2. So this is the ratio. So now what we are going to assume is that this venturi is inserted into an air stream with an unknown velocity V1. Now, with regards to this venturi itself, the most direct quantity that can be measured when we know we are having an venturi that we are considering, the most direct quantity what we can measure is the pressure difference, P1 minus P2. Now, how do we measure this pressure difference in actual, since then we are talking about this pressure difference and measuring of pressure difference, right? How do we go about that? So what we do is, usually we place a small hole or pressure tap in the wall of the venturi at both inlet and the throat and connect the pressure leads, that is the tubes, from these holes to a differential pressure gauge. So we place the holes at the inlet and the throat and put pressure tubes over here and connect that to a differential pressure gauge, or we connect it to a U-tube manometer. So with the help of this setup, we are able to calculate or obtain the pressure difference directly, that is P1 minus P2. Now let us relate this pressure to this unknown velocity V1 using the Bernoulli's equation. How we can do that? Let us have a look. So now from the Bernoulli's equation, if I were to write V1, so I can write it as V1 square is equal to 2 by rho P2 minus P1 plus V2 square. Let us say this is our equation 8. Now from continuity equation that we had for our incompressible flow, we had written, can I write V2 is equal to A1 by A2 into V1, that is from this equation, correct? Let us say this is our equation 9. If I substitute this equation 9 in equation 8, what do we get? V1 square as 2 by rho P2 minus P1 A1 by A2 whole square V1 square. Now the task is to solve for for V1. Upon solving this equation 10 for V1, this is the term that we get, which is our equation 11. Now this equation 11 is giving me the inlet air velocity in terms of pressure difference, known density and area ratio. We usually consider these quantities to be known. So can I say from this equation that we can use a venturi meter to measure the air speed, that is the air which is entering the duct, correct? But usually in today's date, the most common measuring airspeed instrument is the pitot tube. But venturi still has some applications in some general aviation, small general aviation airplanes, maybe home built or simple experimental aircrafts which you have. In such cases, venturi is still used, but the most used one would be the pitot tube. Now, how is this pitot tube used and what is the speciality of pitot tube? Let us have a look. And we are going to have a look at it with the help of one of the most important experimental setup used by aerodynamicists, that is the wind tunnel. So, which is one of the application of incompressible flow, that is the low speed wind tunnel. So here we are going to consider an low speed wind tunnel, which is an application of incompressible flow. Now, what is a low speed wind tunnel? It is nothing but a large venturi where the airflow is driven by a fan which is connected by a motor. As you can see over here, we have a fan which is connected by a motor. What are these fan blades? They are nothing but they are similar to the propeller blades, not exactly, but they are a little bit similar to the airplane propellers what we have, and they are designed to draw the air inside the wind tunnel, airflow into the wind tunnel circuit. Now, as you can see in these figures, we have two types of wind tunnel. One is the open circuit wind tunnel and other one is the closed circuit wind tunnel. Now, what happens in this open circuit wind tunnel? We take the air from the atmosphere and give it back to the atmosphere directly. And in case of closed circuit wind tunnel, what is happening? Whatever the air is coming from the exhaust is again sent back to the inlet as an inlet air, or the air coming inside the wind tunnel. Now, in both the cases, you can see over here in the open circuit wind tunnel, you have a settling chamber, then the nozzle, then the test section, and then the diffuser. Similarly, in the closed circuit wind tunnel as well, this is the settling chamber after the motor and the fan. This area would be your settling chamber, nozzle, test section, diffuser. So in both the cases, what is happening? The airflow is entering with pressure P1 and velocity V1 in the nozzle where the area is A1. Correct? And when this nozzle converges into the small area which is known as our test section, where we place our aerodynamic model. So this is your test section. You can see we have an aerodynamic model placed in the wind tunnel. So as this air passes through the aerodynamic model, it flows into the diffuser. Now, when it is coming from the nozzle to the test section, what happens to the pressure over here? Because it is converging to small area A2. What happens to the velocity? There is a rise in velocity and decrement in pressure. In both the cases, we can see that in the test section, the area is decreasing, velocity is increasing, and pressure is decreasing in the test section. Now, as the air passes through the aerodynamic model, that is, it flows over an aerodynamic model, whatever we have placed in the test section, it moves to the diversion section, which is our diffuser, where there is a increment in area, decrement in velocity, and increment in pressure. Now, from the continuity equation, if I have to write velocity in the test section using the continuity equation, so we can write V2 is equal to A1 by A2 into V1. Let us say this is our equation 12. Similarly, what if I have to write for the diffuser? So in a similar fashion, for the diffuser, we can write V3 is equal to A2 by A3 into V2. This would be our equation 13. Now, if I want to look at the pressure at various locations in the wind tunnel, I can relate it to the velocity. The pressure at various locations can be related to velocity by using Bernoulli's equation. So what do we have the equation as? P1 plus half rho 1 V1 square, which is equal to P2 plus half rho V2 square, which is equal to P3 half rho V3 square. Now you see that I have written as only rho without putting any subscript 1, 2, 3 because we are considering that the flow is incompressible over here. As we said, low speed wind tunnels are applications of incompressible flows. So my density would be constant in all the three sections. That is, it would be equal. Let us say this is our equation 4. Now, what is the basic factor that controls this air velocity? as we have seen previously the formula for V1 that we had derived. So the main factor that controls the air velocity in the test section is nothing but the pressure difference, P1 minus P2. So if I rewrite this equation 14 for V2, let us say we have V2 square is equal to 2 by rho into P1 minus P2 plus V1 square. This would be our equation 15. Now let us substitute equation 12. So from equation 12, where we had V2, from that we are going to take V1 from this equation. So if I take V1 from this equation over here, what would be V1 would be equal to A2 by A1 into V2. So this V1 term we are going to substitute over here. Upon substitution, we have 2 by rho P1 minus P2 plus A2 by A1 whole square into V2 square. So that is, we have got V2 over here. So let us see how we can manipulate this equation. Upon manipulating and solving for V2, the term that we get is under root 2 into P1 minus P2 divided by rho into 1 minus A2 by A1 whole square. This is our equation 17. This seems a little similar to what we had calculated for the inlet velocity, correct? Little bit similar, right? So this equation 17, what does this equation 17 say? It demonstrates the test section velocity V2, that it is governed by the pressure difference P1 minus P2. And over here, the area ratio that we have, that is A2 by A1, it is a fixed quantity for a wind tunnel. So when we take a wind tunnel, it is a fixed quantity for that particular wind tunnel design, the area ratio. And density, it is a known constant, that is for incompressible flow. Now the fan that you have in this wind tunnel, which is driving the wind tunnel flow, this fan is creating a pressure difference by doing the work on the air. So what usually happens is, when the wind tunnel operator turns the control knob of the wind tunnel and adjusts the power of the fan, what they are usually doing when they do this is they are adjusting the pressure difference. And when this pressure difference is adjusted, in turn, using the equation 17, the pressure difference is adjusted, so the pressure difference will be calculated, and using this equation I can calculate the velocity in the test section as well. So usually in the low speed wind tunnels, the measurement of pressure difference is usually done by the means of using a manometer. Now here the density what we are talking is not the density of the liquid in the manometer, keep that in your mind. It is the density of the air in the wind tunnel, so do not get confused. Now there is one more term if we have to consider, that is the product of rho and g. If I consider this product, which is also the weight per unit volume of the manometer fluid, let us denote this by W. So we had one equation previously which is for the manometers, where equation. Now what is this equation which we had already taken from the manometer readings? If I connect, that is the side of the manometer associated with PA, where the ambient pressure is taken, is connected to a pressure tap in the settling chamber of the wind tunnel. This is the settling chamber. If we connect it is connected, that is PA is connected to the pressure tap in the settling chamber of this wind tunnel, then we get the pressure as P1. So if I connect PA, it would be P1 if I connect it to the settling chamber pressure tab. And at the other side of the manometer, which is associated with PB, if I connect that to the test section pressure tab, that is over here. If I connect that to the test section pressure tab, that is over here, then I would get the pressure P2. So if I'm getting P1 and P2, how can I write this equation? So in terms of P1 and P2, I can write this as P1 minus P2 is equal to rho G delta H. What is rho G? W. So we can also write it as P1 minus P2 is equal to W delta H. So what is this delta H? It is the difference between the heights of the liquid on the two sides of the manometer. So based on this, I can write my equation 17, that is V2, as under root 2 W delta H by rho into 1 minus A2 by A1 whole square. Correct. Now, what is the use of manometer? As we can see, it is used to measure the pressure difference. But these manometers were used date back, like long days ago. But today, in most of the wind tunnels, they have been replaced by an array of electronic pressure measuring instruments. But manometers are a good example in application of fluid static. Most of the low speed wind tunnels, the test section is vented to the surrounding atmosphere by means of slots in the wall. So this is in some of the wind tunnels. Now, the equations that we have discussed over here for this particular wind tunnel, what we call it as the quasi one-dimensional flow equations, these have certain limitations, and these are in exact known as quasi one-dimensional inviscid flow equations. All right. Now these equations can be misleading when you're solving some real life aerodynamic problems. How they can be misleading, let us have a look. For example, if I say A3 is equal to A1, okay, that is inlet area of the tunnel is equal to exit area of the tunnel, which means if I say A3 is equal to A1, that is V3 is equal to V1. So this we get from equation 12 and 13, correct? We get V3 is equal to V1, that is V3 would be equal to V2, and ultimately V2 would be equal to V1, which means V3 would be equal to V1. That is one thing. So if I say V3 is equal to V1, then what we can observe from equation 14? That will tell me that P3 would be equal to P1. That is, the pressure at the exit is equal to pressure at the inlet, which means there is no pressure difference in the entire circuit. So if there is no pressure difference in the entire circuit, that is the wind tunnel, if that was existing in real, what would happen? What would be the case? The application would run without any power. We would not require any power, and it would be a perpetual motion machine, which is not possible, because in reality there are losses in the airflow due to the friction at the tunnel walls, and also there is a drag on the aerodynamic model in the test section. So it is not possible that we will have P3 is equal to P1. There would be pressure difference existing. Now here comes some of the drawbacks, maybe, let us say, for the Bernoulli's equation. So the drawback is that the Bernoulli's equation does not take these losses into account. That is, whatever are the losses taking place because of the friction at the wall, Bernoulli's equation is not taking them into account. That is, it is not considering them. Also, the second point is that viscous effects are neglected in the Bernoulli's equation. Correct? Now, in an actual wind tunnel, there is a pressure loss due to viscous and drag effects. So, which means my P3 would be certainly less than P1. Therefore, the function of the wind tunnel motor and fan is to add power to the airflow in order to increase the pressure of the flow that is coming out of the diffuser, and it can be exhausted to the atmosphere or it can be returned to the inlet in case of a closed circuit wind tunnel. So this was all about the limitations or drawbacks of Bernoulli's equation, about manometer and venturi, how we measure the pressure difference and how we measure the flow velocity with the help of the mathematical formulae, and how we measure the pressure difference by using the YouTube manometer, and how it is done in the wind tunnels. So in our next lecture, we would be coming with one more interesting topic. So thank you for listening. Stay tuned.